Well, we're getting things down to the wire here. We're just about done with our chapter 7. So we're going to move on to 7.4, talk a little bit about something called length of curves, and then we're going to do a little step backwards again to pick up 7.4d tomorrow. But I feel like if you know the lengths of curves, that'll help you out with 7.4d. So we're going to talk about how to find out how long a curve is in its measurement, as long as the curve is smooth. And then what do we do if we do have vertical tangents or corners or cusps which make the curve not smooth anymore? How do we handle that? So let's just quick review the length of a straight line. And so again, if we are measuring, from x1, y1 to x2, y2, we use the Pythagorean theorem to measure the lengths of the legs so that we can come up with a measurement for length of L. So looking at the length of the base, so that would be x2 minus x1 quantity squared, and the length of the height, which would be the difference of the y's, that would lead us to the length of the hypotenuse. And so then the hypotenuse would be the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. And to kind of make the connection to calculus, the difference between the two x's is the differential of x. And the difference between the two y's is the differential on y. So we would say the square root of dx quantity squared plus dy quantity squared. So that's how you find the length of any straight line segment. So now the question becomes, well, how do you find it if it's a curve overall? And really a curve, if you zoom in, is just a whole bunch of little straight lines all connected together to make it a curve. So if we pull this down to a microscopic scale, and we're looking at things really, really, really small, then it's going to essentially look linear. And so the length of an arc would be the addition of all of those little incremental lengths, all those little hypotenuses added together. And assuming that we're going, from one little hypotenuse to n hypotenuse and the limit as n approaches infinity. So this becomes an overall integral, as we have an infinite summation that really is the definition of an integral. And so the length of an integral curve from a to b is the square root of quantity dx squared plus quantity dy squared. Now we're going to multiply this integral creatively by the number 1. And so we divide each of the differentials by dx. Okay? But that differential is within parentheses. And so to keep it balanced, if we're going to mathematically invite 1, if we divide everything by a dx quantity, we also have to multiply everything by a dx quantity. So we need to multiply everything by dx quantity squared as well and extend it over our square root. So this is just multiplying the problem by 1 by dividing and multiplying by the same number. Okay, so now I'm going to split this up and clean it up. So I'm going to make this its own separate square root. And then I'm going to simplify the whole expression. So we are looking at L being equal to the integral from a to b of the square root of, all right, now this quantity, dx divided by dx quantity squared, is just 1. And then the next quantity is dy divided by dx, quantity squared. And then this, the square root of something squared, is dx. And so the length overall is the integral from a to b of the square root of 1 plus the derivative squared with respect to the x-axis, so dx. So that is the more familiar expression of how to find the length of any curve. So let's apply it to this parabola. All right, so this parabola is going to be going from 0 to 1, and we want to find out how long is it from a to b. So the length of this curve would be from 0 to 1 of the square root of 1 plus the derivative, so 2x, quantity squared, dx. In other words, the square root of 1 plus 4x squared dx. Most of these integrals you will not need to do by hand. Once you have the integral set up, then you can use a Math 9 feature to integrate that to find the numerical integral using your calculator. Okay, we're just going to practice the setup today, but you would not necessarily need to solve this by hand. All right, how about a length of the curve of a sine wave? All right, so here's our sine wave from 0 to 2 pi. We know that if we just did a straight out integral from 0 to 2 pi of the sine of x dx, that should come out to be 0 because the area above and the area below cancel each other out. But what if we want to measure the length of the curve? Now you can do this two ways. You can do the whole thing from 0 to 2 pi, or you could just measure from 0 to pi and then double it. It's really your choice on how you want to do that. If we want to find the length, you could go from 0 to 2 pi and then the square root of 1 plus the derivative of sine, which is the cosine of x, quantity squared dx. Or we could use symmetry and we could just go from 0 to pi and then make sure that we double it so that we have the length. Okay, again, the emphasis is on setting up the integral, and then you'll just use a Math 9 to evaluate the length. All right, how do you get around a corner? So let's start with a simple corner with an absolute value. So this absolute value is moved 1 to the left. So we're at -1. And we want to know the length of this curve from -2 to +1. So we're looking at the length of the curve that would go from -2 and then turn the corner and go to +1. So how long is that? Well, this is not a curve. Okay, these are straight pieces. So we could use simple geometry to help us find out how long each piece is. So using the Pythagorean theorem, we know that this is the square root of 2. And by symmetry, this would also be the square root of 2, and so is that, the square root of 2. So altogether, the length of this curve is 3 square root 2. But what if these are not linear pieces? Okay, the other way you would set this up is just to break it up into chunks. You would go from -2 to -1, and you would integrate the absolute, the square root of 1 plus the derivative. Okay, now the derivative of the absolute value on this section has a slope that is negative, so the slope is -1 squared dx. Okay, plus the integral from -1 to +1 of the integral 1 plus, and then the slope is 1 this time, dx. And so this confirms what we had geometrically. It's the integral from -2 to -1 of the square root of 2 dx, which is a constant, and then from -1 to +1, the square root of 2 dx, which is another constant. And so we get the exact same expression of 3 rad 2. So if you're trying to get around a corner, the calculus is to split it up at the corner. And so let's consider the equation x to the 2/3. So this graph is not differentiable at 0. And if we want to go from -2 to +1, so we want to make sure that we're measuring this part of the curve and that part of the curve. So we want to either use symmetry or break this up into pieces. So there's a couple ways that you could do this. You could break it up into segments from -2 to 0. L equals, okay, and the length would be 1 plus, and the derivative, 2/3 x to the -1/3, that whole quantity squared dx. And then plus, from 0 to 1, and then the same derivative, that quantity squared dx. So that's one way you could use the broken up sections to your advantage. You could also set it up this way and go from -2 to -1. So that would be just this segment right here, kind of break it at -1 of the integral 1 plus 2/3 x to the -1/3 quantity squared, and then break it up again into the next piece that goes to the origin. So that would go from -1 to 0. And then the final piece, which goes from 0 to 1, by symmetry is the same as the piece you just did previously, so you could double that. So that would be another way you could set it up. It still takes 2 integrals. You just break it up in different pieces or use symmetry to your advantage. Okay, x to the 1/3. This is a problem where we have a vertical tangent. And so x to the 1/3 is a graph that comes up and is vertically tangent at the origin and then heads out that way. And so the problem is that the derivative would not be defined at 0. So normally we'd want to break this up at 0, but the problem is that the derivative is not defined there. It's not part of the domain. So we're going to integrate this in terms of y instead. And so going from -1, -1, and then out to 8, 2, so that would be out here. We just would want to think of this in terms of y instead of in terms of x. And so we will change our equation, and our equation would be x equals y cubed. And so then the integral would go from the y value of -1 to the y value of 2. And the derivative would be 1 plus the derivative of y, which is 3, or the derivative of the expression of y cubed, 3y squared, quantity squared, and then make sure you integrate that in terms of y. Okay, so then you're avoiding the issue of the vertical tangent by integrating it in the terms of y instead. And so the derivative would be defined at the 0 instead. So this isn't hard. The setup is really not hard. Use the Math 9 to integrate it. Just know how to use symmetry, how to use bounds creatively to get around problems like corners or cusps or vertical tangents, and then you should be good to go. And so then I will see you guys on Tuesday.